Hey, P Statistics. So in this section, the last section of Chapter 4 on gathering data, we're going to be looking at using studies wisely. And so this is a very important topic just for life, just knowing how to, what conclusions can we actually draw based on our study? What can we comfortably conclude and what can't we comfortably conclude? So, and by the end of this section, you should be able to explain the concept of sampling variability when making inference about a population and how sample sizes affect sampling variability. Explain the meaning of statistically significant in the context of an experiment and use simulation to determine if the results of an experiment are statistically significant. And then the next part, identify when it is appropriate to make an inference about a population, when it's appropriate to make an inference about cause-effect, and evaluate if a statistical study has been carried out in an ethical manner. Actually, we're going to leave that part off. We've talked a little bit about ethics, but this is not an AP topic, so if you want to read up more on that, check that out. All right, so inference for sampling. Inference is the idea of like what conclusion can we draw? We're going to infer from our sample, what can we infer about the population? And so when the members of a sample are selected at random from a population, we can use the sample results to make inferences about the population. As long as they were drawn from that population. Even when making an inference from a random sample, it would be surprising if the estimate from the sample was exactly equal to the truth about the population. So whatever our mean is for our sample, that won't be exactly what the population mean is. We expect a little bit of sampling variability, right? That sample may be a little higher or a little lower just because of the chance, because of the sampling variability, the randomness associated with this. And so this is the idea that if you repeated that process again and got another random sample, you're going to get a different set of individuals from that population, and you're going to get a different estimate. So if you keep measuring the mean, you're going to get different X bars each time. If you keep measuring a proportion, you'll get different sample proportions each time. It won't be the exact same every time. And so we got to recognize that in our sample. A lot of times people publish these statistics that they get like they're the truth, like this is exactly what it is. But in reality, realize there's a little bit of variability there. Might be a bit higher or lower. And so we'll eventually get into what do we do with that? We have these confidence intervals and so on. We'll get to later on in the class. So sampling variability associates with sample size. The larger the random sample is, that tend to produce estimates that are closer to the true population value than smaller random samples. So they're more precise. They're not more accurate. So here, looking at these plots here, they're both centered at the right spot. So presumably, okay, we're doing a percent of red beads, and presumably the population proportion is actually 30%. And what they've done here is they've simulated a bunch of different samples. And these were samples of size 20. And so we see in one sample of 20, we had 50% that came out. In like one sample, we had 10%, or a few samples, we had 10%. On average, it is 30%. So this method is not inaccurate. It's just imprecise. It's less precise than if we get a larger sample. If we get a sample of 100, we're not as likely to get half of them, right? So we're going to typically expect those values they'll tend to be closer to the actual population estimates. So we can always get more precision by increasing the sample size. All right, so example of this. How much do National Football League players weigh on average? In a random sample of 50 NFL players, the average weight is 244 pounds. Do you think that 244 pounds is the true average weight of all NFL players? Explain your answer. So is that exactly what the population mean is? That sample mean, that statistic, is that exactly what their population parameter is? No, it's not. Probably not. Technically, it's possible we got really lucky and got right on the head, but most likely not. Different samples of size 50 would produce different average weights, so it would be surprising if this exactment is equal to the true average weight of all NFL players. That said, NFL, the 50 is a pretty decent size. We expect it probably to be pretty close. So which would be more likely to give an estimate close to the true value weight? Sample of 50 or random sample of 100? The answer is 100 because estimates tend to be closer to the truth when the sample size is larger. And so that's the idea with sampling. We're going to get a lot more into that later on in the year, but we kind of want to make sure that we have that knowledge of sampling variability. Don't forget about sampling variability, and that if you repeated the same sample again, if you got 50 football players, you get one mean, you get another random sample of 50 players, you get a slightly different mean. They'll both probably be pretty close to the population mean as long as that sample size is large. So then what about experiments? Well-designed experiments allow us to infer about cause and effect. That's ultimately the conclusion we're going to draw. So in an experiment, there are two ways to explain why the average response for one group is different than the average response for another group. One possibility is that the treatment had no effect whatsoever, and that the difference between the groups is just chance variation because of the randomness of assignment. If we did no treatments, say we want to, study how well people do on a test, and we're studying maybe you had treatments where you're going to do one class this way, another class this way, or something like that, and we want to look at the differences. Well, if we did nothing different, you're going to see differences between them anyways, just because of the random assignment. Some students that were going to perform better on the test might just happen to get assigned to group A or group B, and that will cause those results to be a little bit different. So when you get your results and you see a slightly higher value for one, slightly higher value for the other, that doesn't necessarily mean cause and effect. It could be, but we can't be sure. It could just be randomness. So the other possibility is that the treatment actually causes that difference. If you see a difference between the values, maybe the treatment caused it. So how do we decide? Well, sometimes it's hard to know, but what we want to look for, what really helps us be certain, is when the observed results of a study are too unusual to be explained by chance alone, we call it statistically significant. There's a statistically significant difference between them, those two numbers, that it's unlikely that it was just chance, that randomness. And so we're going to have to study some randomness in the next couple of chapters so that we can calculate what is the probability that it'd be off by this much and that much, and then ultimately draw our conclusion. So an example of this is talking on a cell phone while driving more distracting than talking to a passenger. David Strayer and his colleagues at the University of Utah designed an experiment to help answer this question. They used 48 undergraduate students of subjects. The researchers randomly assigned half of the subjects to drive in a simulator while talking on a cell phone, and the other half to drive in a simulator while talking to a passenger. The simulator, we do simulations sometimes just so people don't actually get hurt, right? And kind of a representation of reality, but it's not quite real, so that people don't get hurt. One response variable was whether or not the driver stopped at a rest area, and that was specified by researchers before the simulation started. The table shows the results. So we got our two treatment groups, our cell phone group and our passenger group. Notice we got 24 in each of those. And then we had people that stopped at the rest area or didn't stop. So of our cell phone passengers, 12 stopped and 12 didn't. When they were talking to the passenger, 21 stopped and 3 didn't. And so overall we got our totals there. We got our two-way table. So it's been a little while since we looked at one of those. So what they said is calculate the difference here in proportion, the difference passenger minus cell phone in the proportion of students who stopped at the rest area in the two groups. So our proportion of passengers that stopped was 21 out of 24. And then our proportion of cell phone users was 12 out of 24. So we're going to subtract those two numbers. So 21 out of 24 minus 12 out of 24, so 87% minus 50%. Ultimately, the difference was 37%, or 37.5%. So people who were talking to passengers were 37% more likely to stop than the cell phone users. That's what we could say. That's the difference. All right. And so they did a simulation of this, and so let me grab this simulation hunt. So 100 trials of a simulation were performed to see what differences in proportions would occur due to only to chance variation in the random assignment. Assuming the type of distraction did not affect whether a subject stopped in the rest area, that is 33 stoppers and 15 non-stoppers were randomly assigned to the two groups of 24. So ultimately, that's what we're going to look at here. Let me pull this up. All right, so here we go. Here is the simulation that they actually did. They simulated, what was it? 100 trials of a simulation. So there's 100 dots here. And so that they looked at was, they took the actual data values and they randomly assigned them to the two treatment groups and then looked at the difference in proportion. And so a computer does that, and that's really nice to have a computer to do that process. So we've got dots here where the proportion was higher. Passenger minus car, a cell phone, the proportion was lower. And so these are all like simulated differences in those results. So there are 3 dots at 0.29. Explain what these dots mean in this context. 0.29 are these 3 dots right here. That means in 3 out of 100 trials, or 3% of the time, we saw a difference where the passengers stopped that much more by chance, right? So that they were 30% more likely, almost 30% more likely to stop at this rest area. So that is, that's what those dots represent. All right, or to put it in their terms, when we assumed that the type of distraction doesn't matter, there were 3 simulated random assignments where the difference in the proportion of students who stopped at the rest area was 0.29. So then part C, use the results of the simulation to determine if the difference in proportions from part A is statistically significant. And so remember, statistically significant is that it's unlikely to happen due to chance. And remember, our difference was 0.375, which did not show up on this chart. It's 0.375 is off the chart there. So it's unlikely to happen by chance. And so then the conclusion that we can draw here is because the difference of 0.375 is or greater never occurred in the simulation, the difference is statistically significant. It is extremely unlikely to get a difference this big simply due to chance variation in the random assignment. And so we looked at that through simulation to look at kind of what differences would we happen. They randomized them into treatments and looked at the difference. They randomized, and again, if we just got those numbers, they kind of re-randomized them into groups. We'll eventually be able to do this theoretically with some probability calculations, but for now we can just look at it through simulation and kind of see, in this case, it was off the charts, so it is statistically significant.